Hello and welcome to section 2. This section is all about the properties of water and cell membranes. We touched a little bit on cell membranes in our last unit when we talked about the macromolecule of lipids and specifically phospholipids. So we're going to delve into more on the cell membrane, but first let's talk about some water because water holds tons of potential for biological life on Earth as we know it. So without water, everything you know wouldn't be happening right now. So let's talk about water, and then we'll get to cell membranes and all the wonderful things that those cell membranes do to control passage of molecules in and out of the cell, keep our cells at the right concentration that they need to be. We're going to learn all about that. So go ahead and break out your notes. Let's talk about some water right now. So as in typical fashion, we're going to start with our outline. Roman numeral 1 is all about water. First thing we're going to talk about with water, you already know the chemical formula for water. It's H2O, obviously. Let's talk about the structure and how that, everything in biology, how the structure leads to its function. If the water molecule had a different structure, it would have a completely different function. So thankfully, it has the structure it has. So let's talk about the structure of water. And here's what's super important about water. Water is a polar molecule. And here's what a polar molecule means. It means that if something is polarized, you have opposite ends going on there. So I want you to think of a battery or the poles of the Earth. There's a top end and a bottom end. On a battery, you have a plus end and a minus end. It's polarized. That polarization allows water to do its job so well. So first thing under the structure of water, water is a polar molecule. And here's what that means. Being polar means that you have opposite ends and with opposite charges. So you have ends with opposite charges. That's what polar means. And here's what water looks like. You already know water is H2O. So here's what the structure actually looks like. You have an oxygen, and oxygen, if you look on your periodic table, it has 6 electrons. So if you're looking at oxygen, it would have 1, 2, 3, 4, 5, 6. And these 2 lone pair electrons right there, or these 2 not lone pair, but lone electrons right there, are going to conveniently bind with another hydrogen. And to make it look nicer, we're just going to write it straight up and down with the bonds, because each line represents 2 electrons. So that's water. Here's what makes water polar. The natural shape of water is bent. That's what we call it in the chemistry world. So if you're trying to name the structure of any chemical compound, you can honestly, there's a whole bunch of, we call these VSEPR geometry, and this one is specifically bent. It's obviously bent. But what makes it bent are these 2 lone pairs of electrons on oxygen. Those lone pairs are really actually huge electron clouds that are pushing those hydrogen atoms down. So these large electron clouds, although it doesn't look large because they're just 2 little dots, but here's the deal. You don't know where those 2 little dots on either side of this oxygen are hanging out. So they're taking up this huge electron space, meanwhile pushing those hydrogen atoms down. And the other neat thing about oxygen and hydrogen, it's interaction. Oxygen loves electrons. It actually desires to have all the electrons it can. It has 6 to begin with, but it wanted those extra 2 from hydrogen because 6 plus 2 is 8, and that's where oxygen is happiest. So what oxygen does, it grabs those other two electrons from hydrogen and pulls it really close to itself. We call that electronegativity. It's the desire to have electrons near you. Oxygen is way more electronegative than hydrogen. Oxygen has a little bit more mass than hydrogen. Hydrogen just has 1 electron. It's content with 2. It's okay to give or take its electron. It loves sharing if it can. So whenever you see electrons being shared between 2 atoms, that's called a covalent bond. In this case, This is called a polar covalent bond, because what oxygen is doing, if you want to imagine, here's an electron from hydrogen, here's an electron from oxygen. This electron from hydrogen is actually a little bit closer to oxygen right there. It's pulling it closer to it. So same thing is happening here. They're sharing the electrons, but they're just a little bit closer to oxygen. So what that does to oxygen, it's recruiting these electrons closer to itself. In a sense, it's recruiting negativity, because electrons are negatively charged. So if I have more negative particles around me, I have what we call in water, we call that a partial negative. That little lowercase delta for that little squiggly sign, that's a lowercase delta. We call that partial negative. So this is partial negative. And you can guess, since hydrogens, they're not holding their electrons close to them, they're actually releasing them a little bit farther away from themselves, they're no longer as negative as they once were. So if you're not negative, you're now becoming more positive. So the hydrogens carry a partial positive charge. And that's what gives water its polarity. You have this partial negative end and this partial positive end on the side, on the bottom, or on hydrogen. So oxygen is always partially negative. Hydrogens are always partially positive. Now you can see how opposites are going to start attracting to each other to start building like a whole bunch of water put together, because water doesn't come in individual compound molecules. It comes together, all held together beautifully. So let's talk about how that works. I'm just going to erase this for a moment. We're going to redraw water again. But what I want you to know is that water actually attracts itself to itself because hydrogen bonds between water molecules allow them to stay attracted to one another. So hydrogen bonds exist between water molecules. And here's what that would look like. If I have my oxygen and my hydrogens, I got my partial negative here, my partial positive, partial positive. This partial negative on the oxygen is going to be attracted to a nearby water molecule like that, because my hydrogens are partially positive and so forth. These partial positives on the hydrogens are going to be attracted to another nearby water molecule, specifically the oxygen side, because the oxygen is partially negative. You can keep this going out until you have a huge web of water, or I don't know, the ocean, if you want to go there, because that's how water works. It actually is attracted to itself through these intermolecular forces that are keeping it together. So this right here, that is a hydrogen bond. Hydrogen bonds, we mentioned this before in the last section, they're super weak, very, very weak. They're about a 20th of the strength of a covalent bond. You see covalent bonds within water. There's a covalent bond between oxygen and hydrogen, and that's strong. You can't take apart a molecule of water, but what you can do is break apart water molecules from itself, It takes energy, but you can do that. Hydrogen is easily broken in that respect. Hydrogen can only bond with certain elements as well. So hydrogen can only do carbon, hydrogen, oxygen, and nitrogen. Those are the only elements hydrogen can make a hydrogen bond with. So you can have, that's what the hydrogen bonds with those guys. So you automatically have all these hydrogen bonds going around here. So if I wanted to extend this one over, I would have water going here, and you could just keep going and going and going with how that works. At about 37 degrees Celsius, which is about 98.6 degrees Fahrenheit, same as your body temperature, you have about About 15% of the water molecules that are residing at 37 degrees Celsius, one water molecule will be covered by four other water molecules. So this one would be like that. And that doesn't last long. It's about 15% of your water. It looks like that when it's at that temperature. That's pretty hot. When you lower the temperature, it becomes more stable and you see stuff like that. So let's talk about the properties of water. So the big things I want you to know about water, the structure of water, is that it's polar. You have ends with opposite charges. These covalent bonds between oxygen and hydrogen are super strong, but they are polar covalent bonds, and the overall structure of water is very polar. It's as polar as you can get. So this overall structure is polar. These bonds are polar covalent. However, between water molecules, you have hydrogen bonds that are existing there to allow it to have all the properties we're about to talk about. Okay? So that's for the structure of water. Let's go to big letter B, the properties of water, which essentially almost relates to the function of water. So whenever we talk about the properties of anything, it's almost saying, how does it behave in a way? So here we go, properties of water. Some of these you know because you interact with water all the time. So the first property that we're going to talk about, we've already kind of discussed it a little bit, is called cohesion. So cohesion, this is the binding together of water molecules due to hydrogen bonds. So the ability of water to bind to itself, essentially. So the binding together of water via hydrogen bonds. Now the best example of cohesion, and if you could think about it, is surface tension. So one example of cohesion is surface tension. Water has a very high surface tension, high enough that you could see bugs skirt along water in a pond. You could make many things float. That also has to do with the surface area of the object you're talking about, of course. But that surface tension of water is huge. And it's all because many hydrogen bonds are linking together all these different water molecules. And it takes a little bit of strength to break that many bonds at once. And so that's why the surface area of the object that is resting on the water has a big deal to play. Something flat would just kind of smush the water and it doesn't break those hydrogen bonds. Something short or more pointed and more steep, that would go literally cut right through the water. So surface tension is the measure of how difficult it is to stretch or break the surface of a liquid. So just for a definition of surface tension, it's the measure of, I want to make sure I said this right for you, measure of how difficult it is, to stretch or break the surface of a liquid. So that's surface tension. Measure of how difficult it is to stretch or break the surface of a liquid. So that's cohesion, and one example is surface tension. Another example of a property of water is something called adhesion. Adhesion is something you're very familiar with if you've ever played around with water enough. It's the clinging of water to another surface. The clinging of water to another surface. A great example of adhesion is something called capillary action. Have you ever oh goodness, play with straws in your water, and you could kind of see the water and the straw kind of creep up the sides a little bit. That would be adhesion. If you put a napkin into water, just dip the tip of the napkin in the water, eventually the water creeps up the napkin. That's adhesion. It's because the polarity and the hydrogen bonds within water are allowing that property to happen. That water just naturally has that ability because of its polarity to actually do that. And the hydrogen bonds are kind of just holding together the water and pulling it up as it goes up. So that's adhesion. Another property of water we have is specific heat, specifically high specific heat. So the high specific heat of water. And there's a number for this. You have 4.19 joules per gram degree Celsius. You're like, what in the world does that mean? If you haven't had chemistry yet, this is what it is. It basically says joules is a measurement of energy. It takes 4.19 joules, a measurement of energy, to raise 1 gram of water 1 degree Celsius. That's actually a lot. Most liquids out there don't have that high enough specific heat. But it is a blessing in many, many ways because the high specific heat of water prevents water from boiling away too easily. It helps resist temperature changes and absorbs and releases allows it to absorb and release heat well. So it helps resist temperature changes because it takes a lot of energy to change the temperature in water. So when water actually freezes, that's a big deal. Or when water actually boils, that's a big deal. It means that you've overcome all those hydrogen bonds when you're trying to boil water. You've overcome all those hydrogen bonds to literally vaporize a molecule of water away from the group that was liquid at one point. So high specific heat of water is great. That means our oceans don't freeze, which is great. Some parts do because they're on the poles and they get that cold, but our oceans also contain salt. And whenever you add a substance to water, we call that a solute. When you add that to water, it actually lowers the freezing point, so it takes a whole lot more energy to freeze salt water than it would to be freezing pure water. So this high specific heat of water, that's a good thing. We want that. Another great thing that we love about water, and we're going to erase this so we have some room. Number 4 is if you ever pour yourself a nice glass of iced tea or lemonade, you have ice cubes in there. What happens to those ice cubes? Are they sinking or are they floating? Hopefully, if everything's working well, you have floating ice. So ice floats. That's huge because if ice sunk, don't worry about your drinks. I'm not worried about the drinks that you're drinking. Like if you have ice and it sinks in your Coke, that's no big deal. Think of the oceans and the lakes and the rivers and everything else where we see water. If you have a lake and your ice and it freezes over in the winter, that ice is freezing up on top and it actually floats up. And here's why. The hydrogen bonds that are within your water, they stretch out dramatically. You don't see this with normal other liquids. They actually kind of contract in. So this is something, and it makes this beautiful crystalline structure. I don't have enough room to draw it on the board, but you could get the picture that instead of these hydrogen bonds being close and kind of liquidy and fluidy, what happens is they actually stretch out as far as they possibly can. And that's what makes ice float, because if I'm not so compact, I'm not that dense. I am less dense when there's a little bit space between me and my neighbor. So the ice is less dense than water. That is the big thing. So ice floats because, I'm going to erase this water, ice is less dense than water, than liquid water. So imagine if you have a river or a pond or something that freezes over in the winter, if that ice was more dense than liquid water, that ice would sink to the bottom. that would kill all the plant life growing in the ponds or in the rivers, and eventually that would affect the ocean dwelling organisms such as fish and whatever else you have growing in there. So if ice sunk, that would be really, really bad. So it's a great thing that ice is less dense than water. All right, one more thing, one more property of water, and we'll be done with the property of waters. So water, last one is water is the universal solvent. What a solvent is, it's a dissolving agent. So if you want to dissolve salt to make a solution of salt water, you would add water to it. That would be obviously salt water. But water has the ability to take apart sodium and chloride in a crystalline form. So sodium chloride is table salt, and actually splits them up into individual atoms, or ions, if you will. So the ability of water to be a universal solvent, it's not completely universal. This is really for only certain types of compounds. So it can readily, for the most part, dissolves other polar molecules, because it can recognize it, or ionic compounds. Now, the ionic compounds, that's just chemistry language. If you haven't had your chemistry background yet, here's what that means. So, NaCl, that's sodium chloride. Sodium and chloride, they come together really well because sodium has a +1 charge, chloride has a -1 charge. Sodium actually donated an electron to chloride to make it negative, and since it lost a negative, it becomes +1. So when it's solid like this, when it's in its solid form, that's an S, this is what we call table salt. Add some water to the mix, and since water, you have your partial negatives and your partial positives, this partial negative is going to be attracted to that sodium ion, because negative and positives will attract. These hydrogen ions, or atoms, are going to be attracted to this chloride ion. So here's what salt water actually looks like inside a glass of salt water. I would have free floating sodium ions all surrounded by oxygen, like water would be just all over the place surrounding this, because its partial negative is just attracted to this positive charge on the sodium right there. Chloride would also, they actually split, and then they receive their charges. This chloride is going to be attracted to all these hydrogen ions, or atoms, forgive me, from the water because of that negative charge. That's what salt water actually looks like. You just can't see it because it's so small. So those are the properties of water, my friends. We have 5 properties of water. We got cohesion, adhesion, we got specific heat, we got ice is less dense than water, we have the universal solvent for water, that beautiful property of it. So a lot of, all of these properties, if one of them was not working the way it is, chances are we would be having a different biology lesson right now, because life would be different as we know it. So that's why whenever we do space exploration or anything like that, if they find water or remnants of ice on a plant, or on a planet, that's a big deal, because they're wondering what else is out there. But as far as we know, we haven't found anything. But the fact that water can exist outside of our planet, that's pretty cool to think of. And so knowing that, how important it is for us for survival, it's a good thing to learn about. So come on back. That's it for water. We're going to move forward to cell membranes on the next lesson. See you soon.